Hola, bienvenidos a todos al coloquio. Hoy tenemos con nosotros a Sean McCurdy, que trabaja aquí en el Instituto de Matemáticas desde hace como 6 semanas. Y nos va a hablar sobre, no sé cómo se dice eso en español, varifolios. Okay. Yeah.
Varifolds. Thank you very much for the invitation. Thank you all for coming. It's a real pleasure and an honor to be here. How many people have heard of varifolds before? Excellent. Perfect. Okay. So I'm going to introduce varifolds, but I'm going to do so in a very biased way through these geometric variational problems. So let's start with those. Geometrical variation problems are a part of the calculus of variations, right? Where you're trying to look at functionals, which instead of looking at properties of functions, right, now you're trying to look at minimizers or critical points of functionals that involve some geometric quantity, right? Maybe this is the length of a curve, maybe this is the surface area or the volume. There are lots of problems like this. One of the most famous, classical, is the isoperimetric problem, right, where you are trying to for a fixed volume, you're trying to find the shape that has the smallest surface area, right? So volume, surface area, very geometric. Or the dual problem for a fixed surface area, you're trying to maximize the volume, right? These are these quantities that are involved. Also problems like the existence of geodesics, the shortest curve, right? This is also a geometric variational problem. And then there's a very wide class of problems which get a little bit fuzzy around the edges. You could think of the brachistochrome problem as an example of this. This is finding a curve where if you have a ball that rolls along that curve, you want the curve that will give you the shortest amount of time. So you're not exactly minimizing the length, but you're minimizing a quantity, the time, which involves the geometry of the curve, and this is this is a geometric thing, which I'm going to consider something like the length, right? There's also lots of problems which we call free discontinuity problems. This shows up in image segmentation, where you're trying to minimize something that looks like a weighted volume on a set of full dimension, and then also the size of a lower dimensional set, maybe like the surface area, where you allow your function to jump, something like this. This is a very large class of problems. And then, of course, shape optimization problems, I think, also properly fall into these geometric quantities. But this is a very biased introduction to this field. So we're going to focus on one of the most famous examples of geometric variational problems, the so-called Plateau's problem. Plateau's problem was introduced like over 40 years before Plateau was even born by Lagrange. And he asked the question, given some simple closed curve, maybe given here by this wire, right, does there exist a minimal surface which spans that curve? Right? So this was called Plateau's problem because in the 1800s he looked at this problem through the example of soap films, right? So you bend a wire, dip it in soap film, and then the surface tension pulls the soap film taut and gives an example of something very close to a minimal surface. But the problem itself is as stated here, and notice that this is an existence question, right? Of all the surfaces which span this curve, that have this curve as their boundary, right? Does there exist one which is minimal among all of those, right? So it's helpful to have a little bit of review of how existence goes in the calculus of variations. So we can look at a little toy example about solving the Dirichlet problem, right? We could, let's say, consider some nice class C of C2 functions, functions with second derivatives which are continuous, and maybe we'll fix some very nice function on the boundary of a very nice domain, smooth, why not? And we can consider the Dirichlet energy, which is going to measure, in some sense, how wildly the function oscillates. And this is the calculus of variations. So we could think of like differential calculus. If we have the graph of some function, we want to find minima, or at least critical points. What do? We take the derivative. We see where the derivative is 0. Well, this functional has as its domain, well, let's say at least this collection of functions. So when we wiggle in the domain, right, much like we would for differential calculus, right, maybe by choosing some phi which is compactly supported, at least C2, something like this, right, we get this expression, right? This is what's functional is going to change when we vary by phi, in the phi direction. And since I've chosen all of my v to be C2, well, we can do, right, the divergence theorem, and we can get this expression. And so if we have a critical point, like a minimum, say, right, then we would expect the derivative to be 0, which means that we would expect this quantity to be 0, and this would tell us that this Laplacian of phi, the Laplacian of v, right, should be 0, right? So we should get a harmonic function, which hopefully has the right boundary values, and we would have solved the Dirichlet problem. One way to do it. But this is a huge if. If we have a solution in this class that is a minimum, how do we go about getting a minimizer? Well, one idea would be to just take a minimizing sequence in this class and hope that it converges to something that should be the minimizer. But you immediately run into the problem that, of course, C2 functions need not converge to another C2 function, right? Things can go horribly wrong. You need Sobolev spaces, et cetera, et cetera. Well, what we've just tried to do is Nelly's direct method in the calculus of variations, and we've run into one of the problems, or one of the things that it requires in order to work. First, we need a class that's large enough for some form of compactness, right? This is where, in the previous example, actually we should have considered Sobolev functions, right? And in taking this class larger, usually this involves lowering the amount of regularity required, right? And the second thing that we need is we need lower semi-continuity of the functional under the convergence given by compactness, so that when we take our minimizing sequence, the value of the functional doesn't jump up, right? It can only go down. And this will guarantee that we get a minimum, right? Okay, and the trade-off here is that we get existence by enlarging our class to include much rougher things, and so we lose regularity. And the challenge then becomes to work to show that the minimizer that we find is actually nicer than the ambient class, right? It actually has the kind of regularity that we sort of expect it to. Does this make sense? Okay. So in the context of varifolds, I have some work ongoing that is in varifold regularity, but that is highly technical and perhaps not best suited for a wider audience. And so I have decided to introduce varifolds to you through their role in the existence theory, right? And sort of the thesis of this talk is, what is a varifold? Well, varifolds are the natural framework for obtaining existence in a wide variety of geometric variational problems. We're going to focus on the plateaus problem, and I'm going to try to convince you of this by looking at the history of frameworks through which people have tried to and successfully solve the plateaus problem, and look at those frameworks not so much in the great theorems that came out of them, but just from this perspective of the calculus of variations and geometric measure theory. What are their strengths? What are their weaknesses? And we'll see how varifolds in many ways provide what I think of as the most natural context for this. They have lots of good properties. So that's what this talk is about. Okay. So, plateaus problem. The first solutions that we have came from in the 1930s with the work of Rado and Douglas. Douglas actually won the first Fields Medal for this work. And so we'll follow his format a little bit. And the framework that they had was, well, we have our curve in space, maybe, and then he's going to look at some R, some two-dimensional manifold with boundary A, and he's going to look at maps from R, right, into a larger Euclidean space, right, where the boundary is mapped homeomorphically or the boundary A here is mapped homeomorphically onto the curve that we're given, right? And then he's going to minimize within this class. That's the setup. And this has a lot of strengths. This is a lot of beauty to it. One, there's no question about what the boundary means or what spanning means, right? We have a nice manifold. Its boundary is mapped to the boundary. Naturally, in the image, right, the curve is spanned by the image of the manifold. Minimization actually occurs over parameterizations of the boundary and then extended inside to an even nicer map. And because these maps are so nice, smooth, there's actually no question about what we mean by surface area, right? They don't get so impossibly difficult that you have to raise questions about, ooh, does surface area make sense here? So the main quantities in the problem are defined in a very natural, easy way. This is a great strength, very intuitive. And then from a technical perspective, the compactness that we need and the lower semi-continuity that we need follow analogously to Sobolev theory, right? As they might for solving the Dirichlet problem in our toy problem. And so the direct method gives existence in this framework. But it also has some weaknesses. First off, because we're only considering a fixed manifold R, comparison is only restricted to surfaces of the same topological type as R, right? And if the problem was among all surfaces, is there one with minimal area? This feels like an arbitrary topological restriction, right? Secondly, the method of extending the map along the boundary to the interior fundamentally relies upon complex analysis, right? And the thing that he minimizes, once he finds a minimizer, the fact that it actually minimizes area fundamentally depends upon the existence of isothermal coordinates. Again, complex analysis, and therefore this entire method is restricted to two-dimensional surfaces. And it's a very natural question to ask, what about higher dimensions? Right? And that's a limitation. And I know that I said that the naturalness of the definition of surface area and boundary and spanning were strengths, but they're also weaknesses because they really hide very deep questions about what it means to be the boundary, what does it mean to be surface area, what does it mean to be spanning, that we're sort of hiding as you go to higher dimensions. Right? So these are some problems. To face these problems, we might think, there was a lot of these problems that depended upon the parameterization. So let's get rid of the parameterization and let's just think about sets, right? So the whole notion of m-dimensional surface area turns out in the work in the 1930s and 1940s, we figured out that this really kind of depends upon parameterization. Let's throw it out and instead deal with the m-dimensional Hausdorff measure. It's a very natural sense of m-dimensional measure. And instead of the convergence of functions, right, and maps, let's consider convergence of sets under, say, the Hausdorff distance. It's a nice bilateral comparison of sets. And so this is the approach taken in 1960 by Reifenberg, and his framework for Plateau's problem says, okay, well, instead of a curve, maybe let's just let gamma be a compact set, maybe represented here by the black, right? And the class that I'm going to minimize within, well, maybe that's going to be all compact sets which span this boundary. And there's a little asterisk here, and I'll talk a little bit about why that's there, but at least for now, at minimum, the notion of spanning should be that the set S, maybe here in pink, I guess, should at least include, right, the set gamma, right, as the boundary. Okay, so this is his framework, and this has a lot of strengths to it, right? If we're just talking about sets, it's no problem for higher dimensions. That's great. Also, the notion of boundary is kind of naturally built into the class. I'll say a little bit more about how. But this notion of containment, very natural for sets. Compactness, or sorry, compact sets are complete under the Hausdorff distance, so compactness is kind of right there. Convergence in the Hausdorff distance is very natural for compact sets, so all of these things are very natural notions for the setting. And under this setting, Reifenberg is able to obtain a minimizer. He's able to obtain solutions to Plateau's problem. So this is a great success. And maybe the minimal set is this sort of much smoother object, right? But there are some problems. Notably, the m-dimensional Hausdorff measure is not lower semi-continuous with respect to the Hausdorff distance convergence. I have a little picture here illustrating why. You can imagine smooth images of the sphere, right? Sort of bent and twisted, and a sequence of these images getting a little bit more spiky, sort of space filling, right? But where the area goes to 0. You just make the tubes thinner, the area goes down. And this might converge because it might become dense in the sphere, converge to the solid ball. And so you would have a sequence of surfaces, right, whose area goes to 0, but whose limit is the solid ball. And this is one of the key problems with the notion of like surface area, is that if you insist upon lower semi-continuity, then the set itself ceases to have any sort of notion of, inherent notion of surface area. It really depends in some sense on the approximating sequence. And so you could say that the solid three-dimensional ball, in fact, has 0 two-dimensional surface area. This makes very little sense. So sets are really not the natural class for this kind of problem if we insist upon lower semi-continuity, which we really want to do for Tonelli's direct method of the calculus of variations. Okay, so these are some big drawbacks to the set theoretic approach inaugurated by Reifenberg. And I would say, as a last note to that asterisk, also the notion of spanning and what it takes to be a set where there's going to be a non-trivial solution. In Reifenberg's approach, all of this is done in the language of algebraic topology. And this is very natural in some sense. The question of what does it mean to be a boundary is a natural topological question. But as an analyst, I'd prefer a more analytic or maybe even measure theoretic notion of boundary. So even though it's very beautiful and very appropriate, as an analyst, I want something else. Okay. So for a different approach, right, we might start with a smooth submanifold and realize that, okay, well, this smooth submanifold has a submanifold I can do sort of differential geometric integration theory, right? And I can realize that, okay, this smooth submanifold is actually a continuous linear functional on the space of compactly supported smooth two-forms, right? Sort of differential geometry approach. And another way to say this sentence is to say that this sigma is a two-dimensional current, right, in the sense of Durand currents, things like this. And then we can realize the area not by integration against like the area form, but as the supremum of integration against these smooth compactly supported two forms where we restrict the co-mass, technical stuff, right? And if we look at it this way, right, viewing these surfaces as elements of a dual space, right, then we should really give up convergence in sort of this Hausdorff metric, this very geometric set theoretic convergence, and maybe we should think of convergence as currents, which is to say convergence as elements in a dual space, which is to say weak star convergence, right? This is a lot of very natural approaches, natural advantages to it. And this is really the approach to Plateau's problem put forward by Federer and Fleming in 1960, although the sort of idea in many ways goes back to Cacciapoli in 1927 and DeGiorgi in the 1950s, where he solved the isoparametric problem. And if you're interested in that isoparametric problem and the solution by DeGiorgi, I'm teaching, hopefully, a class next semester on exactly that. So if you're interested, please come. But the basic idea is to construct some favored class of nice surfaces. Nice surfaces, maybe they're just triangulations, right? Sort of collections of triangles that we put together to form some nice surface, right? And on that nice class, it's very easy to define surface area, boundary, all of these things, and to look at those as objects, right, which are currents. And then we're going to take the closure of that class under this weak star convergence, and that's the class that we're going to minimize in. Right? We just take the closure in the appropriate notion of convergence, and then extend our notion of surface area from the elements in the favored class to the full enlarged class simply by density and lower semi-continuity. So we just force our functional for whatever it means to be surface area to be lower semi-continuous by definition. Right? And this is very natural in many ways. It allows for higher dimensions, no problem. The boundary is built into the class because if you start with your nice surfaces with fixed boundary and take the limit, right, anything that you get will have, in a very intuitive way, the same boundary. For technical reasons, you could also, for the boundary, through Stokes' theorem, but I'm not going to get into current theory at the moment. Completeness is built into the class. We built it to be complete by taking the completion, right? Lower semi-continuity is built into the area functional. That's how we defined it to be lower semi-continuous. So there's a lot of beautiful natural structure to the framework to approach the problem. And of course, the Banach-Alaoglu theorem gives compactness for mass-bounded subsets, and this allows us to use the direct method of the calculus of variations in order to get existence of a minimizer. So solutions for Plateau's problem exist in this framework. And as a further strength, if you start from this differential geometric perspective, then I will point out that also for two-dimensional currents in R3, like we had in our picture, minimizers have no singularities, right? They're perfectly smooth, so you can think of them as sort of nice manifolds in the differential geometric sense. Life is good. But there are also drawbacks to this framework. One of the weaknesses is that currents have orientation, right? In order to build your differential geometric integration theory on manifolds, you need an orientable manifold, right? So you can only consider oriented competitors, and maybe you want to consider surfaces which are not oriented. Those seem like perfectly reasonable competitors for surface area. But the real problem is that orientation leads to cancellation. If I have two lines and I orient them oppositely, I can take, and when I go to the limit, I don't get maybe a density 2 line. The orientations cancel each other out and you get nothing, right? So you can have mass evaporate, and this maybe isn't a problem when you're considering minimizers, if we think about sort of the Morse theory picture. But this is a rather big problem when we want to consider critical points, because this evaporation of mass means that no Paley-Smale condition is possible in this class, and that's one of the key assumptions for like the mountain pass theorem, things like this. So if you want to consider critical points of the area functional, maybe not minimal surfaces, but just surfaces which are critical points, then this is a difficult class to consider that within, right? For calculus of variations reasons, right? This is kind of a big problem. And as my last example of a weakness, I want to also repeat that two-dimensional currents in R3 have no singularities. This is a strength from the differential geometry perspective, because you may not like singularities, but if you actually dip a wire in soap film, you'll see very often these sort of Y shaped singularities. They show up all the time with angle it's like 120 degrees between them, right? These show up. And so we would expect minimizers, even in two-dimensional surfaces, in 3 dimensions, to have these kinds of singularities, because when you do the experiment, they're there, right? And this framework does not allow for this kind of singularity, simply because there's no way to orient, right? Like there's no way to orient this space, right? So they get rid of a very natural class of singularities that we may want our theory to account for. Okay. So strengths and weaknesses of this version of the functional analytic approach. But now let's take what I think of as a more measure-theoretic approach. We'll start with our same smooth submanifold, and rather than thinking of it as an element of the dual of 2 forms, right, smooth, compactly supported space, instead, let's just think of it as a measure, right, where it's the 2-dimensional Hausdorff measure just restricted to the set that it is. And we can very naturally think of, well, what's the area of a certain subset A? Well, it's just that measure of A. It's a very, very down-to-earth approach. So this will give us a radon measure. Radon measures are just measures which are finite on compactly supported, on compact subsets, and also behave very well with the topology. There's good approximation results. Borel sets are all measurable. Lots of good properties. Looking at this surface as a measure means that we're thinking of it actually as a radon measure, and it turns out, of course, that radon measures, right, are the dual to compactly supported functions, which are continuous on Rn. So again, we have this dual framework, right? And so the duality here given for a given compactly supported continuous function, right, is just integration with respect to the measure, right? And this measure theoretic perspective, looking at radon measures as the dual to this space, this is where varifolds come from, right? I have not defined a varifold yet, but this is where they come from. But to see them in their full generality and to put all the pieces in place is going to take just a little bit of work. So I'll give the full definition. Young, in 1951, introduced something he called generalized surfaces, which were then modified slightly by Almgren in 65, 66, and then sort of a very beautiful version of the theory came out in 72 with the work of Allard. And the idea that they were developing is this for varifolds. Letting m and n be integers and letting u just be some nice open set in Rn, and we're going to let G and M be the Grassmannian of M-planes in Rn, right? So it's just a nice smooth manifold where each point is a different m-dimensional linear subspace of Rn, right? Then we're going to define an m-dimensional varifold V in this open set U to just be a radon measure on the product U in the sort of Euclidean coordinate, and then the Grassmannian of M-planes in Rn. So you can think of it as one coordinate is Euclidean space, and the other coordinate tells you a particular m-dimensional plane, linear subspace. If we don't like this Grassmannian component, well, we can just forget about it. We can project it away, and every varifold has an associated measure, which we call the mass of the varifold, which is just defined upon the Euclidean space where we project away the Grassmannian component, right? So this gives us a nice radon measure on Euclidean space, and this is where we're going to get our notion of surface area eventually from. Okay. So examples of two-dimensional varifolds. Two-dimensional, because I can put pictures of things like that up. One example is our previous example. We can look at a nice smooth submanifold. We can look at it as a pair of the set itself and some density function where integration with respect to the varifold is just given by integration with respect to the area in the Euclidean perspective, maybe weighted by this density function. And then in the Grassmannian component, maybe we just put a Dirac delta function on the particular tangent plane, right, to the point in question. Right? So it's a very natural sense. And of course, when we look at the mass, we sort of project away this Grassmannian component, and this is just the weighted area of the submanifold. Very, very natural. Right? But there are other examples of two-dimensional varifolds. We could take a cloud of points, right? Put little Dirac masses on each of them, and for each of them say, oh, I want to associate a different particular two-plane, right? To approximate maybe a surface. This is very useful in sort of numerical projects and shape analysis, things like this. And so I can form a nice varifold this way, and of course, the mass, I just project away the particular two planes that I've chosen. And another example of a two-dimensional varifold is maybe I take the three-dimensional cube, right, and in the Euclidean component, just integrate with respect to the three-dimensional sort of Hausdorff measure, and maybe I choose a single plane for every single point, right, that's a two-dimensional plane. And that's going to be the measure in the Grassmannian component. Why do I have these examples up? To emphasize in the definition, right, that whether or not you're an m-dimensional varifold does not depend upon sort of what the support looks like in your Euclidean component. It only depends upon which Grassmannian you're looking at. So as long as you're taking two-dimensional planes that's your Grassmannian, then you're a two-dimensional varifold, no matter what the structure or size of your induced sort of mass measure is. Okay, so this leads to some very natural questions, right? First, how do we obtain good structure on the support of the mass? This is the Euclidean component. If I say I have a two-dimensional varifold, then maybe I want the support to be a two-dimensional object, right? We can also ask, how do we talk about the boundary? It's a measure. What does it mean to be the boundary of a measure? How do we get something like this to attack Plateau's problem with? And also, do we really need the Grassmannian portion? Is that not just abstraction gone wrong, right? So to answer all three of these questions actually comes from the calculus of variations, from taking the first variation of the varifold. So let's bring it down to a very, hopefully very easy example. Let's suppose we have a nice C2 submanifold, maybe represented by this perfect picture. And let's pick a nice vector field along which we're going to sort of perturb, right, this C2 submanifold. And then we're going to take the first variation, which is just the derivative of the area, right, among this family of sort of perturbed surfaces, right, where we're perturbing according to the vector field phi that we've chosen. And we're going to get that this is equal to the integral along the entire surface, right, of the divergence of phi, where the divergence is now taken with respect to, at a point x, is taken with respect to the plane, right, the tangent plane of the surface at point x. So this will change depending upon which point we have, right? And if this first variation is bounded among all possible, right, C1 with compact support vector fields that we choose, as long as they are bounded by 1, then this is a bounded linear functional on this space by density, et cetera, et cetera. The Ries representation theorem tells us that actually this first variation is representable, right, by integration against a particular radon measure. And in this picture, this radon measure is going to have two parts to it. One, which is like going to be on the surface itself, where this will just be the mean curvature, right? I guess in this, the way I've written it now, it'll give us information about the mean curvature. Right? Technically, this is a vector, and so like the density of it will give us the magnitude of the way I've written it. Is a little bit non-ideal to say. But one part will give us information on the mean curvature, maybe represented by these red vectors, and another part will give us information about the boundary. It will be integration along the boundary of the normal. Right? So those are the two parts. And so we see the boundary begin to show up, right, in this measure theoretic sense. Right? So extending this idea to the varifold, the measure which is the varifold, we can look at the first variation of the varifold, which is just the derivative of the mass, which we should think of as giving us the surface area, right? That's the thing we care about. And it turns out that we get this integration along, oh, sorry, that should not be there. That's a copy-paste error. Sorry about that. We're integrating with respect to the varifold of the divergence of phi now along the different Grassmannians, right, weighted by the varifold, right? So maybe there are multiple hyperplanes at a single point. Maybe they have different weights. The measure of the varifold tells us how to do this. And so this is why we cannot get rid of the Grassmannian component, right? It is essential information for the first variation. Okay. Also, if the first variation is bounded, for the exact same reasons as before, the Ries representation theorem tells us that it's representable, right, by integration against some radon measure, right? Who knows what it looks like? Well, to get the boundary, we can just look at whatever that radon measure is and take the part of it which is absolutely continuous to the mass. This will give us the information about the mean curvature, in this case called the generalized mean curvature, right? And then we'll get some part which is singular, and that is going to be the boundary, right? So it comes out of the measure theory, right? And this gives us a beautiful measure theoretic and functional analytic notion of the boundary, which as an analyst, oh, good. This is, now we're cooking, right? This starts to feel like home. So now we know what the boundary is. The last question I had asked was about good structure. How do we talk about the structure of the support of the mass? Well, if the first variation is bounded and the density with respect to the dimension m is bounded away from 0, then, well, we get representability for free from just the first variation being bounded. But with this extra density condition, actually it shows that there exists some m rectifiable set sigma and some nice function, by which I just mean like measurable, doesn't have to be super nice, theta, such that the mass, which we should think of as the surface area, that's the information that we want, is actually just this weighted integral against the m-dimensional measure on this nice m-dimensional rectifiable set. And rectifiable sets are a really natural class of object in geometric measure theory. Right, we'll say that sigma is, let's say, countably m rectifiable, right? This is a definition, right? Well, if there exists some countable class of maps F, right, which are C1, right? So if Fi is in, I guess, C1, right, such that sigma is merely contained in the union of Fi, I'm doing m-dimensional, right? Right? So to be an m-rectifiable set, you just have to be a subset of some countable union of C1 images of Rn, right? So things can get pretty crazy, but at least you know you have tangents almost everywhere, your density will exist. Well, I guess it could be infinite. But you definitely get tangents almost everywhere. This is a very nice class of functions. And this is unfortunately sort of like, at this stage, kind of the best you can do abstractly, right? Of course, there are further regularity theorems, but this is going to be our version of, well, at least we get a nice rectifiable set. It's not too crazy. Okay, so with these things in place, we can now approach this varifold framework with which to solve Plateau's problem. So given some simple closed curve, or indeed some higher dimensional variant, but for ease, let's just stick with the curve, right? our minimizing class is just going to be the collection of varifolds such that, one, we want our first variation to be representable by integration. That means it's locally bounded, right? This is going to give us our notion of a boundary. Right? We want the density to be bigger than or equal to 1 almost everywhere. This is because we're dealing with measures, and if I take one measure and just multiply it by 1/2, I have another measure, and that would lower the surface area, and I could multiply it by 1/2 again. So this is a way to normalize it, to make sure we're talking about something that corresponds to surface area. So these two together will give us good structure. They will give us a notion of a boundary. And we're going to assume that this boundary measure is essentially carried by our curve. This is sort of a measure theoretic notion of saying that it's not quite the supports, but you can think of it as like the support of this measure is sort of the same as the curve. It's just a measure theoretic notion of this. And we're going to assume that, okay, our mass and our first variation are bounded. Right? This is going to be our minimizing class. Right? And this approach has lots of strengths. Right? It allows for higher dimensions, no problem. Again, the Banach-Alaoglu theorem implies that this class is compact in the sense of weak convergence of measures, so we get a very natural sense of compactness. We have lower semi-continuity of the mass under weak convergence of measures very naturally. And we also have a very, from my perspective, natural functional analytic and measure theoretic notion of the boundary. And so Tonelli's direct method will give us existence of minimizers, right? This is a good framework, right? But perhaps more importantly, from the perspective of the calculus of variations, right, there's no issue of orientation or cancellation. So we can consider critical points of the area functional in a very natural way. And varifolds were introduced by Almgren in 1966 to study these critical points of the area functional, right? Also, there's absolutely no constraints on the genus or any sort of topological type in our class of comparisons. And also, in some sense, right, these sets and also Feder and Fleming's currents are all naturally can be viewed as varifolds themselves, right? It's sort of a larger class that contains all these other approaches that we've talked about. So in this sense, right, this is my pitch for why varifolds are sort of this very natural, beautiful class to approach geometrical variational problems. Okay. But I've talked about weaknesses for everyone else, and so I have to talk about the weaknesses of the varifold approach. And in my opinion, the weakness is that it can just be really technical, especially when it comes to questions of regularity, right? We focus today on the frameworks by which we would obtain existence in these problems, but remember that the direct method of the calculus of variations has this trade-off, right? Enlarging our class to sort of more irregular objects, we obtain compactness, we obtain existence, and then we have to do the hard work of showing that that minimizer that we got actually has higher regularity than the ambient class. And so all of the hard work is in doing the regularity theory, and for varifolds, this becomes extremely technical. With the last few minutes that I have, I'm going to do a very brief sort of overview of one part of this regularity theory. And I want to point out first off that like what it means to be regular for a varifold, we usually just mean, what does it mean for the support of the mass, right? So we're not taking the full Euclidean plus Grassmannian portion, right? We're just looking at the support of the Euclidean portion. What does that look like? That's a set. What can we say about it? Right? And there's a bunch of different ways to approach this. We can look at the infinitesimal picture. We can try to ask questions about what blow-ups look like. A blow-up, right, is just a process of sort of zooming in and finding like a tangent object. So if I have some nice curve, maybe I pick a point, right? A blow-up is just this process of like zooming in do I have? Right, and then maybe I zoom in again. I'm running into different things, right? But you sort of zoom in, you keep stretching it, and you limit object, in this case, obviously. Yeah, just straight line, the tangent line. But you can do a process like this for measures. You can do a process like this for sets. And so you can begin to classify what your blowups look like. This is a very interesting avenue. You can ask questions about, like, well, if I know I have a tangent object that's flat, at what rate does almost every point converge to flat? And there are a number of different ways to measure, right? Like, what is converging to flat? This is also another beautiful area of Varifold regularity with a lot of work in it. In the time that I have remaining, I'm going to focus on this local parametric perspective, which is to say, when can the support be parametrized by some nice map from Euclidean space? And how nice can we assume that map is, right? But there's other questions in regularity that have to do with the singular structure, which is to say, what can we say about the set where maybe we have these Y singularities, or there are other types of singularities, right? Is that set nice in some sense? How regular is that set itself as a lower dimensional object? Okay, but we're going to focus on this local parametric picture. Probably the most famous, one slide to go, sorry. To do this, we're going to make some standing assumptions. First, we're going to assume that our Varifold has locally bounded integration. We all know that this means that by the Ries representation theorem, right, the first variation is then representable by integration. We're going to make the next assumption, which is to say that maybe in the ball that we're considering, there's no boundary, right? So we're looking interior, and we're going to get then that we only see this generalized mean curvature portion of it, right? And we're going to assume that the generalized mean curvature is in some nice LP space. So the question becomes, well, what's the relationship between the P, the M, right, and the regularity? And the most famous example of a result like this is Allard's regularity theorem, came out in 1972. And it says that if we have a nice Varifold under our assumptions, and the P is strictly bigger than M, so we're in supercritical dimension. P is greater than the dimension of the Varifold. And we have some assumptions which tell us that in some sense the Varifold is very close to a single disk, right? Then, in fact, as long as this epsilon is small enough, as long as we have not enough mean curvature, then, in fact, there's some function which is in a Holder space, like C1 alpha, right, such that the support is the image, locally the image of this C1 alpha map. So, of course, a very nice result, because now we get to think of the support not as the support of some crazy measure, but we know that, okay, geometrically, it's the graph of a C1 alpha function. It's very nice. In the case of Plateau's problem, you actually know that the mean curvature is 0. And so this plus some like Schauder theory lets you get that actually in Plateau's problem, you actually get smooth images. But this is more general, right? So for general varifolds, what can we say about the regularity depending upon the behavior of the mean curvature? So the supercritical case, what's the next question, right? What happens in the subcritical case? Well, turns out everything can go wrong. Under the exact same assumptions, but just now assuming that we're in an LP space where P is strictly less than the dimension, it's very easy to cook up examples where the support is highly disconnected, dense in a neighborhood, and this just follows from like taking spheres and like packing them down small enough. Everything works out nicely. And so the support suddenly becomes horrendous. Anything can happen, you can't say anything. At least not from this parametric perspective. There's a whole branch of theory which does this like how closely, or at what rate does it become flat perspective. And there's some very successful results in that, but from the parametric perspective, we're cooked. No idea. Okay, so this leaves, of course, critical case, when both P and M are equal. And this was left basically without any real progress up until last year, when B and Zhao published this really beautiful paper, which says that for two-dimensional varifolds, right, if we assume that the density only takes integer values, then if we assume also the hypothesis of Allard's regularity theorem, this sort of very close to a disk condition, but just now with critical dimensions, and as long as epsilon is sufficiently small, then in fact the support actually admits a bi-Lipschitz parameterization by some function f, which is in W22, right? So it has weak second derivatives, which are square integrable. Life is good, right? And this is a really gorgeous result, but of course, one of the problems is that two dimensions, and it relies again essentially on isothermal coordinates. We're back to this two-dimensional complex analysis problem where we get gorgeous results, but they cannot be extended to higher dimensions. And I guess I will just end by saying that recently I completed the higher dimensional analog where we allow n and m to be arbitrary integers as long as p is equal to m, and we have this very close to a disk assumption. Don't worry about this assumption. I'm not going to talk about it right now, but we obtain then that support is actually the image of some nice function where we're in W1K, so we don't get a holder, a C1 alpha map, but we do get a holder image, and this, the map is at least holder continuous, and this tells us that the support is actually locally Euclidean in the sense that it's homeomorphic to disk. So that is a recent result on this sort of critical exponent case. Lots more work going on in this field, but I think I'm going to end there. I don't want to look at that. I will say thank you very much.
¿Hay preguntas para Sean?
Thank you for the very nice colloquium. And I'm glad that you picked this picture because this is exactly what I wanted to ask about.
Yeah.
Every now and then you put the wire in the soap and you don't get just one bubble. You get several bubbles competing for space with a free boundary in the middle. I mean, how far can you use all these approaches that you have shown us to study this phenomenon?
Yeah, so bubbles, as opposed to just a soap film that gives you like a surface. Once you talk about bubbles, these are examples of constant mean curvature surfaces, and the whole Varifold's framework is productive for constant mean curvature surfaces as well, right? As a very nice framework to study these. Because the geometry that you get, these sort of Y singularities and all of this complicated geometry with the surfaces, like these are not manifolds, right? But realizing them as varifolds is no problem. Okay. So it's a very, very powerful and productive framework to approach these problems as well.
Okay, so the philosophy is not to look this as competing bubbles or competing species, but just one surface, which might have singularities or something.
Yeah. So, I mean, it depends upon how you set up the framework, right? So there are like double bubble problems where you're not trying to model like the surface itself, but the interiors. And these you actually use with, at least the ones that I'd seen, usually use like the current method, which in the full dimensional case is actually just like sets of bounded variation and sets of finite perimeter. Plug for my class next semester, that's what we're doing. But of course, you can realize all of those as varifolds if you want, right? It depends upon, if you set it up as this competition, you want two domains that interact in a certain way. Sometimes, right, sets of finite perimeter are the better way to do it, or at least historically, there's been a lot of work in that. But if you wanted to approach this with the language of varifolds, there's sort of an easy, like, map from that into the varifold setting. Yeah.
Thank you.
¿Hay más preguntas?
Thanks for your nice talk. I'm a little bit curious because you say that in the abstract measure framework, the notion of boundary is natural. But why you say it's natural, why you found it natural?
So in this framework?
Yeah. Yeah.
I find this to be a very natural framework. So this is, sorry, I think I might have misspoken. I find this notion of a boundary to be very natural because it's coming out of the measure theory and because it's coming out of this sort of duality functional analysis representation.
Well,
and that's sort of just like the language that I grew up in math. So to me, this is home, right? But I acknowledge that particularly for the examples in the set theoretic approach, right, where the notion of boundary is just a set, but whether or not you have a non-trivial solution to Plateau's problem is then a problem of algebraic topology. Like, that's also very natural in one sense, but I'm not an algebraic topologist. So I see this and go, oh, I really want the measure theoretic notion of boundary. I really want this other one. So it's very biased in this.
Okay, thanks.
Yeah, sorry.
En español voy a hablar. En el espacio de los conjuntos, respecto de la convergencia esta, distancia h, ¿ha trabajado usted otras topologías en el espacio de conjuntos?
You're gonna have to help me out on that. Sorry.
Gracias, es todo.
In the space, in the convergence. That is a very good question. I have not. I have not actually done. I've read about this. I've read some papers, but I have not like gotten my hands dirty to sort of publish anything in this set theoretic approach. I know that there's still going on work in this framework. I know that there are other notions of what it means to span a boundary, which doesn't use this catch homology. But I think that because you're dealing with sets, right, if you view it as a set, then I have a hard time imagining other notions of convergence than this like Hausdorff distance, right? Once you start to think about right, the set as an element of a dual space to get like maybe weak start, like then you're not thinking about it as a set anymore. You're thinking about it as a measure, right? Which is the Varifold's approach. So I don't know of anyone else in the set theoretic approach who's picked a different notion of convergence. But that's a limitation of my reading. Sorry.
Solamente existe la métrica de Hausdorff. Puede, es decir, la estructura uniforme debida a la métrica, sino hay otras estructuras uniformes que no son por esa métrica. ¿Ha trabajado eso? ¿O intenta trabajarlo? ¿Tiene alguna idea?
I have not seen any work on that, but that is a very good point, and that's a very good question. Yeah, I have not seen it, but that is a very good question.
¿Hay otras preguntas? I had a question. You said that you could include like these Reifenberg sets in the Varifold approach, and there, like, what dimension is the Varifold? Do you pick it? What do you do in the Grassmannian direction?
Yes, I see. So from the generality with which Reifenberg approaches things, it is not entirely clear to me, right, how to do this. But one of the things that Reifenberg does, particularly to get around this problem of like little tendrils like this sort of becoming dense and whatnot, is he has to use a version of what's now usually called like the selection principle, where he takes his minimizing sequence and he says, okay, well, if things start to get bad and start becoming dense, then I'm going to modify it, right, to make it better, but still a minimizing sequence so that he can obtain a result. And these modified, right, examples tend to be, so he's able to show then that, like, in the end, you get a locally Euclidean, almost everywhere solution, although he actually allows for these Y singularities, which is why, right, we have this picture, right, demonstrating that. So the full generality of just like, oh, maybe we have a set with a large blob out here.
Right. No.
Like, I mean, you could just say, okay, well, if I expect it to be two-dimensional, then I just, for the Euclidean space, just take the two-dimensional measure restricted to the set. Who cares if I have a large blob out there? That'll have infinite measure, and therefore definitely not a minimizer, right? And then for the Grassmannian component, well, wherever you have a tangent, you just put the Dirac mass on that, and wherever you don't, if the set is small enough, it's not going to matter. But if you have a really big blob, pick any tangent plane you want, because it's not going to be a minimizer, right? Like, from the perspective of getting existence, like, you can kind of throw those out. So it's not determined. There's an arbitrariness for really bad examples, but for every good example, right, there's a sort of a natural, take the tangent plane, put a Dirac mass on it.
¿Hay alguna otra pregunta? I think I had maybe one last question. I got a little bit lost at the end. Bianju's result.
Yes.
What happens with those Y singularities there?
Sorry, let me take this to
maybe.
There we go.
What does the parametrization?
Right.
Or do they not have integrally valued?
So for space, I have omitted like repeating this large block again and again. So we are in the regularity regime where we're looking at some ball where we've centered it somewhere on the support. We've assumed the density is bigger than or equal to 1 so that things don't get too bad. We've assumed that there's not actually a whole lot more mass than a single disk in that ball.
I see.
And we've assumed that the mean curvature, the generalized mean curvature, is really small in integral. So we're really looking at sort of balls, right, where maybe we just have a little bit of wiggle. And what Allard showed was in such balls, right, the topology of the support is Euclidean, right? There's no singularities like this. There's no like sort of extra domes or caps or anything weird going on. And so under this same starting really close to a disk, can you get weird topology, right? B and Zhao showed that you don't get weird topology, and in fact, the parameterization you get is by Lipschitz, which is very good.
Yeah. So to check if I understood, either condition 3 or condition 4 alone would stop you from centering on a point along the singularity, right?
Yes, certainly condition 3, right, would prevent.
Yeah, there you have like.
Yeah, but this could have generalized mean curvature 0, right? So condition
I thought
4.
the fold was like automatically high curvature or something.
So if it's just the fold by itself, right, then yes, you'll get part of the boundary, right? But it's a directional boundary, right? Like there's a
Oh,
there's a
right,
vector,
right, right, yeah,
and they all
yeah,
cancel.
I see,
Hence the
okay.
120
Yeah, so three.
degrees. Yeah, so with three, three absolutely kills that, right?
Thanks. Si no hay más preguntas, démosle las gracias a Sean de nuevo.
Very much.